Good afternoon. Welcome to SETI Talks, our continuing lecture series here at Microsoft. How many of you in the audience were here last week for the panel session? Did you enjoy that? Was good? We had a lot of fun doing it, and I know that our panelists enjoyed it as well. And I think we'll be doing more of that type of format, as well as experimenting with other kinds of formats. The point is to fundamentally share information and perspectives from the Institute on relevant science, particularly in the areas of astrobiology and astronautics, but more broadly to make that accessible, make it fun, make it interesting. So last week's panel session, I think, was a good example of taking a single question and letting a few of our scientists probe that and have a little dialogue and interaction with the audience. So we hope you enjoyed it. I will let you know that during this Silicon Valley Gives event that we were marking last Tuesday, we did raise a little over $50,000, which is very helpful to support the work of the Institute. So thank you for that, and thank you to those of you who participated and helped us make that goal. So that was great. So we have an interesting talk today from Dr. Angela Zalucha of the SETI Institute. Before that, I'm going to switch off the microphone and switch over to read another little announcement that you might find interesting, relevant to, in fact, today's topic somewhat. So if you have followed the news, you may have seen a press release from NASA today about Kepler and its verification of another 1,284 planets, new planets. Are there other Earths around distant stars? A new analysis of the Kepler data finds more planets, including 10 in the habitable zone. Kepler scientists announced 1,284 newly validated planets, more than doubling the number of exoplanets discovered and validated in the original mission data set. SETI Institute scientists Jeffrey Coughlin and Jason Rowe are part of the scientific team that reassessed the entire catalog of Kepler objects of interest, known as KOIs, to ferret out these new exoplanets. So we have a copy of the NASA press release on our website, as well as a little bit more information about the release. And also there's a kind of a fun little video clip, if you're interested, that shows you, for our regular attendees, you'll have seen this many times before, but it shows you the light curve. It shows you how Kepler works, where the light intensity or brightness of a star that is measured as a exoplanet transits in front of it dims somewhat in a measurable way. What we show is an exaggerated version of that because the amount of dimming from small planets is very, very faint, but Kepler is sensitive enough to detect that. So visit our website at SETI.org to learn more about that Kepler announcement today, and also to see that kind of informative video clip. So with that, let's get into today's topic. We do have lots of questions that come to the Institute, and of course, one of the questions that we get is, what about the stellar occultation data of Pluto's atmosphere? We get that question all the time. So we have a talk today that is titled, what about the stellar occultation data of Pluto's atmosphere? So, in support of our customers and their interests and requests, we're hoping to hit the nail on the head with today's talk. So when Pluto passes in front of a star from the observation point of a ground-based telescopes, we have the opportunity to learn much about its atmosphere, particularly in terms of its temperature profile. Atmospheric characterization of Pluto through ground-based observations, taking advantage of stellar occultation, were taking place long before the New Horizons flyby last July, which of course has taught us and showed us much more about Pluto and its riches. Dr. Zalucha of the SETI Institute will explain this technique and offer comparisons to model data and information sets from other sources. Angela's primary area of interest is modeling planetary atmospheres, Pluto, Mars, Titan, Triton, Venus, and super-Earth exoplanets. She's been modeling Pluto's atmosphere in 3D with explicit circulation, or wind, factored into the models. She points out that wind is very important for weather and climate, but is often neglected because it's hard to model. It's not neglected on our planet, I don't think, but maybe elsewhere. Angela's claim to fame is indeed building these complex models. Angela's been interested in weather from an early age and worked at an AM radio station in the weather department. A broadcaster once joked with her that someday she'd be forecasting the weather for Saturn. Apparently he was right, and she hasn't looked back since. Dr. Zalucha earned a BS in physics from the University of Illinois at Urbana-Champaign in 2000 and a master's and PhD from MIT in atmospheric science, earning her doctorate in 2010. She did postdoctorate work at MIT and was a visitor at the Southwest Research Institute from 2010 to 2012. She joined the SETI Institute in 2012. Angela lives in Boulder, Colorado, and in addition to a passion for planetary weather, she's a volunteer for the Humane Society and quite an avid skier. She's very proud of the fact, and she'll tell you all about this if you give her the chance, that she has now skied for 31 consecutive months, which is why we can never get hold of her, including in the summertime. So this is really consecutive months. And in the summertime, it's a little more challenging because you actually have to hike with your skis to get to where the snow is. So with that introduction, and with hopes of someday skiing on Pluto, let me turn this over to Angela. Angela?
Thank you for that introduction. That was really great. And it is true, I really do want to ski on Pluto. I have a painting in my office, a piece of artwork that says, it's one of those kind of old-timey looking advertisement posters that says, "Ski Pluto, the small planet, it's big on fun." So I'm not joking when they discovered mountains, when the New Horizons probe discovered mountains on Pluto, I was like, oh my gosh, you really can ski on Pluto. So I'm at Mars on that one too. I am not, he's absolutely right. So, like Bill said, the New Horizons probe flew by Pluto about a year ago, so it was last July. And before that, we learned about Pluto's atmosphere through something called stellar occultations, which I'm going to explain in this talk. And so what's bound to happen is when we get all this new data that now we're spoiled with, well, we've got to reconcile it with the old data that we've had since 1988. And it turns out that they don't always quite match. So I'm going to spend pretty much all of the talk talking about all this other data for Pluto that we have, and not so much about the New Horizons. This picture, of course, was try my new laser pointer. This picture, of course, was taken by New Horizons, showing the atmospheric haze that it discovered on Pluto, this kind of blue glow. And that's actually an example of one thing that the stellar occultation light curves, there was a controversy for years and years and years of whether that haze was there, and just a fun piece of trivia, New Horizons found it. So now that argument's over, and we have to figure out what the deal is with all the old data that we had. And I mean the colloquial we, because I'm a little bit too young for some of it. So this is the paper that started it all, dated 1988, June 9, came out June 9, no, the occultation was June 9, 1988. This is the paper that started it all. Jim Elliott, my master's advisor, he actually discovered the atmosphere of Pluto. We had known that Pluto probably had an atmosphere because spectroscopy had shown that there were methane lines on Pluto, but they didn't know if what contribution was from the surface ice and what contribution was from the atmosphere, or both or neither. Well, not neither, but both, one or the other, what each contribution was. It was with this stellar occultation technique that the Pluto's atmosphere was discovered definitively for the first time. Now, there was actually a possible detection in 1985, 3 years before this, by two people in Israel who had their telescope pointed. You'll see in a second that we use telescopes to observe these things. They had their telescopes pointed on almost near the horizon, and it was pointed where the army was firing rockets and generally making stuff explode. And so it was a terrible way to observe with the telescope. And they saw in their telescope when Pluto blinked out of existence, then blinked back in, which is what a stellar occultation is, and I'm going to get to that in a second. But so sometimes people claim that that's the first detection, but this is the first one where they actually took data and published a paper. So a stellar occultation happens when there is a background light source, usually a star, and it's going to be a star for our cases, and this star is shining light to us, the observer, that's your eyeball, and something moves between the star, the light source, and you, and we call that the occulting body. And that occulting body can be usually, for practical purposes, it's going to be something in our solar system. So it's going to be something like another planet, a moon, a dwarf planet, depending on what you consider Pluto to be, and it may or may not have an atmosphere. But from this technique, by observing when this occulting body blocks the starlight, we can learn several things about the occulting body. This is a cartoon diagram of what I just showed. This is our star, again, over here. This is your eyeball now, and what we call the shadow plane. Where the occulting object is the body plane. I've greatly exaggerated here the size of the body and its atmosphere in this kind of blue shading here. So if you want to think about how we observe these, sometimes, well, in the solar system, things are, well, in general, things are all moving relative to each other. So you could think of it as looking at the star and having the occulting body move by, or you can think about yourself being the one traveling through the shadow that this occulting body is casting. So if we're over here in the shadow plane down here, and we're moving through time this way, first we're going to see the starlight coming from the star unimpeded, and we see it at its full intensity, and that's what we're measuring, is the intensity of the starlight, or the flux, technically. As we move through these arrows that I'm using to denote the light, the beams of light coming from the star, you'll see that as they start to hit the atmosphere, because the atmosphere is a gas, it means it's a refractive medium. So that means that it's going to start to bend the light, just like light bends in water or light bends in a prism. And as you get deeper into the atmosphere, the density increases, so it refracts more. And these light rays start to spread out. And when they start to spread out, they decrease in intensity. And we see this drop in intensity as we start to see the edge of the atmosphere of the occulting body move in front of the star. Then eventually there will be the solid surface will be blocking out the star entirely. And then as we come out the other side, we see the atmosphere get less and less dense, and the light rays get closer together and thus more intense, and we see the full starlight pop out the other side. So what's really important is this slope, this drop in light, and exactly how it drops off. That's what's telling us about the atmosphere. I'm going to just flip that image. It's just the same thing. I just flipped it. We're going to be looking at a lot of things that look like this, where here's the full intensity, it drops, here's the atmosphere, and then when it's behind the star. This is what we call a light curve. So when I say a light curve, it's going to be referring to this. So the way that these things are observed is essentially you can think of Pluto's shadow as passing over the Earth. And observers, I'm not an observer, other people go out to fun places like Australia and set up telescopes or use telescopes already in place to observe these things. Now, it's really hard to predict where these happen. There's a lot of observation that goes into it ahead of time, knowing the position of the star and the position of Pluto or whatever's occulting the star. And so they find many, many occultation candidates each year, and a lot of them just end up passing either where there's no people, like over the ocean, or they miss Earth completely. But about every year or so, every other year, we get one that is fortunate enough that the shadow passes over Earth and where there's people. So this one that happened in 2006 happened to go over Australia, and you can see that the Pluto's shadow was only about this wide. This is this bottom boundary and this top boundary. That's how wide Pluto's shadows cast when it came over the Earth. And these dots are where observers had positioned telescopes. Some of these are permanent big telescopes, and some of these are portable telescopes that people carry on airplanes, and they will move around even at the last minute, depending on the weather, or last minute predictions of where Pluto is going to go, to make sure that they're in this occultation path. And it's funny because they have to check, or they have to carry on these telescopes on the airplane, and it's my understanding that it takes a lot of explaining to do as to why you want to carry the 80-pound bag on the airplane and not check it. Well, it's because it's a $20,000 telescope, and that can't be checked. So this is how my colleagues get this occultation data. And I'm going to show you a movie of, this is actually not Pluto, this is an occultation of Titan. It's one of Saturn's moons, but the principle is the same. And there's a few things you want to notice here. First of all, it actually happened to be a double star that went behind Titan, so that means we get two opportunities to see the occultation. But two things are going to happen when the stars start to encounter the atmosphere. The most noticeable one is you're probably going to see an image of the star goes around the limb of the planet. That's usually what people pick out. That's an effect called diffraction, which I didn't really explain because it's not as relevant for getting the atmospheric structure, so I'm not really going to be focusing on it. But what I really want you to notice is as the star sort of hits the edge of the atmosphere, you'll see it dim, and then it will race around the edge and then appear on the other side and get brighter and then go back again. So I'll play it a couple times so you can see. So it's going to start playing. Maybe. Oh, it's already playing here. Okay, here. There we go. Okay, so the first star here hits the atmosphere, it dims, races around the edge, and then brightens again. And here comes the other one. Yeah. So let's play that again, because this always gets, because you gotta look close. Here it comes, wait for it to dim, races around the edge. Now that one dims, races around the edge, and reappears. Okay, I'm still getting a lot of oohs and ahs, so I'll play it one more time. This is the last time, because we gotta move on.
Where was the telescope?
This telescope. Oh yeah, it was on the ground. Yeah. Usually, all of these things are observed from the ground. There have been a few that have been observed by the Hubble Space Telescope, but they're usually on the ground. That's in fact one of the advantages of this technique is that we can do it from the ground, and we don't have to spend we don't spend a lot of money or a potentially high risk mission to send a spacecraft out to a very distant planet. We can do it from right here on the ground and learn quite a lot. So it's a very powerful technique. Okay, let's start talking about atmospheric science. That's my passion. Atmospheric temperature usually. This is an example of Earth's atmosphere, and here on the x-axis I've got temperature and altitude on the y-axis in kilometers, and we call these types of things a temperature profile. So for Earth, it winds around a lot. It decreases and then it increases and decreases, and so Earth is pretty complicated. Here's an example of Mars, the red line. It's a little bit less complicated. It still decreases with height, and then it's kind of isothermal here, and then increases again. And here's an example of Jupiter. I'm not going to go into huge detail of why these things have this shape. Here's Titan, which is, again, a moon of Saturn. We just saw the occultation video for. Kind of almost looks like Earth's atmosphere. It does a lot of winding around based on the different atmospheric species in the atmosphere. And there's Saturn. So you get the picture. These things are all different shapes and sizes. And so what the goal of the stellar occultation technique is to measure the atmospheric temperature, and it doesn't get the whole atmosphere just by the way that this method works. It never gets it's not something that can probe the entire atmosphere. It's usually a section of the atmosphere that we get, like say a section along here. It happens to be where We get Titan occultation profiles. It has to do with things like the atmospheric pressure and some other things. There's you notice there's a difference between like this, which is kind of a line, or at least kind of monotonically increasing, versus this right here, where it turns over, switches directions, and that's going to become important in a minute. I forgot to have a clicker. Oh, Venus, forgot Venus. Now this is Pluto's atmosphere. That was the temperature profile that was observed by the New Horizons radio science experiment, or REX. This is the bottom half of Pluto's atmosphere. You notice it only goes up to 50 kilometers. The things I'm going to be showing actually go up higher. A radio occultation is a little bit different than a stellar occultation. Instead, your background source is radio waves, and you measure the frequency offset of those radio waves. And that's really all I'm going to say about that. But other than that fundamental difference at the beginning, the way that you analyze them is somewhat similar. Okay, do you know where your temperature profiles come from? So with all this New Horizons data coming back, that's really magnificent. People are developing models, and Pluto science is really going strong right now. They get these temperature profiles, and then they tend to compare temperature to temperature. Well, that makes sense because temperature is kind of a thing that we're used to feeling. We feel the temperature in this room. And temperature is what we use in atmospheric models, so it's kind of a natural thing to do rather than this light intensity that I was talking about at the beginning, which is what is actually measured by the telescopes. So somehow we've got to figure out how do we get that light intensity that we've measured to temperature space so we can be comparing apples to apples. And a lot of times people aren't cognizant of the assumptions that went into how that what we observe from the telescope got to be a temperature profile. So I just use this image, which you know where your temperature profiles come from. Your food can come from a lot of different places. Your temperature profiles can come from a lot of different places. So it's good to know where your data is coming from. So back in 1992, in order to deal with the data from that first stellar occultation that was in 1988, or first one observed in 1988, Jim Elliott and Leslie Young came up with a model to describe the temperature of the atmosphere as a function of radius from the planet's center. This is potentially confusing because atmospheric scientists like to describe things in terms of altitude, and astronomers like to describe things in terms of radius. So I'm switching between altitude and radius, but from now on it's going to be radius. But I always put the bottom of my plots at Pluto's surface, which we now know where that is, thanks to the REX radio occultation. So they came up with a model that had the temperature as a function of radius, and it depends on the radius to a power law, which we call B, but I'll just refer to that as usually the power law index. And then there's these two, reference temperature and reference radius. In the model, what we call them is the temperature and radius at half-light. You can just think of them as a reference radius, but what they actually are in the light curve is so where that light curve dropped down, when it was at 50% of its intensity of when the star was not occulted, that's what we call the half-light level, and the temperature and the radius is the temperature and the radius at half-light that corresponds to when the intensity of the light curve is at 50%. But it's just a reference radius. So here's an example of a plot from that model where I varied that power law index, B, and you can see again temperature on the x-axis and radius on the y-axis. And this is just a suite of curves where I varied B from, I think, -10 to 10. And you can see that you can get a very wide array of solutions to this model by varying B. Here's what happens if you vary the reference temperature. Again, this is a good 200 degrees difference in temperature that you can get just over about 200 kilometers of altitude or radius. This is varying the reference radius. Again, a lot of variation depending on what number you use. Now there are more specialized models of Pluto's atmosphere. This one that's built on this very simple functional relationship is, they did that on purpose. They did it so that the math would be nice, so that they could calculate a light curve using algebra and derivatives and calculus, and then so that they could use it for least squares fitting. So this is mathematically constructed. It's not necessarily representative of an atmosphere, because remember, from all those wavy atmospheric profiles I was showing of different planets, those are all things that have been measured by a probe, something in the atmosphere, or at least very close to it. And so maybe you've picked up on that. These don't so much look like, they kind of look like that one. They don't look like this one. But that's what I was saying about where are we on this temperature profile? Like, if we're like along here or along here, then that simple power law might work. If we're on this curve, we're in trouble. So we do have more specialized models of Pluto's atmosphere that actually take physics into account, like radiative transfer of heating and cooling by different species. We know that on Pluto that there's methane and CO at different bands that cause heating and cooling. But New Horizons kind of threw this one out of whack because HCN was discovered on Pluto, and so my colleagues right now, Daryl Strobel and Xuan Zhu, are working to improve this model. So it's going to be a little bit of time before we get back to the physical models of Pluto's atmosphere. And so, yeah, that's what happens when a spacecraft flies by and, ruins your perfect picture of what you thought Pluto was. But they're working on that. So there's another way that we can describe, I'm not going to explain all this math, but there's another way that we can describe the temperature profiles in Pluto's atmosphere, and that's by using the inversion method. And what happens with this method is we have some boundary condition at the top of the atmosphere, and then we can integrate downwards discretely or numerically towards the bottom of the atmosphere. And this method requires no assumption about the shape of what the temperature profile should be. So that's really great, because there are a few assumptions, like the ideal gas law. That's a really, really robust law in atmospheric science, and people aren't going to question that. But there's no assumption that it should be a power law or a logarithm or a squared or a linear or anything like that. The problem comes from this boundary integral region. You need the boundary condition at the top. And where they get the boundary condition is usually from that other model that with the power law that doesn't really describe the shape of an atmosphere that well. So you're kind of stuck with whatever that top boundary condition is. We just don't know. So even though this part's great, if you've got garbage in at the top, you're going to get garbage in at the bottom. So I'll illustrate how that's relevant in a minute. So let me talk about the difference between the forward problem and the inverse problem. The forward problem happens when we have a temperature profile as a function of radius, and it goes through our magic function machine here, and we get a light curve out. And there's one solution for that. For any T of R, for any temperature, there is one light curve. The inverse problem is when we have the light curve, we have this flux. That's what we actually measure. Unfortunately, it's an inverse problem, which means we have to make some assumptions about what the shape of that temperature profile is or the behavior. And often this leads to a non-unique solution that can depend on some shaky assumptions. So that's the problem that we're dealing with when I talk about this inversion method. So what I did was to devise a test. Start with a known temperature profile that I constructed to look a certain way. I calculate the light curve, then I do two different things. I least squares fit it to that power law model. I also tried to invert it using that inversion method, and then I see if I get my original temperature profile back. So the answer is, if either of these two methods works, I should get my original temperature profile back out, because I know what I started with, so I know what I know what the answer is going to be. Of course, when you're observing, you don't know what the temperature is ahead of time. You only are doing the last few steps of this. But so I'm devising a test to start with a known temperature profile, do these mathematical operations on it, and see if we get back out the original answer. Let me go through how to calculate a model light curve. So we start with a model of temperature with height. We use hydrostatic balance and the ideal gas law, which are really, really robust physical laws in the atmosphere, in planetary atmospheres. We convert that to a number density. That's proportional to the refractivity, or the index of refraction. Then, with the laws of geometric optics, this is all 18th century science, laws of geometric optics that were written down for light curves by Chamberlain and Elliott in 1997, we get this set of equations. And you'll notice that, so what we get is a equation for the bending angle of that light ray. Remember from the cartoon diagram at the beginning, how the light rays were bending. We get an expression for that. We get an expression for the derivative of it. And both of these things are needed to construct the equation for the light curve flux. And you notice there's a lot of derivatives going on in here. I'll mention that again in a second. So I kind of have an idea of what Pluto's atmosphere looks like. This is from the physical model that I was talking about that's kind of out of order. This is work I did in 2011 where before the New Horizons flyby, so that was our best guess at the time. And it varied different parameters like the atmospheric pressure, the amount of methane in the atmosphere, and the amount of CO in the atmosphere. And I got temperature profiles that kind of look like this. There's something in common with all of these. The red line is the same in every picture, and the blue dotted line changes. But there's always this sharp increase in temperature near the surface, and then depending on what the concentration of methane and carbon monoxide is, it kind of winds around or gets really cold. But these are different things that happen, such as getting really cold or being colder or warmer systematically. And this is kind of the guide that I'm using to construct my test temperature profiles. Okay, case 1. This is the most basic case, and this is what I'm going to keep referencing back to. I just did the most basic thing to kind of match those temperature profiles from the physical model that I showed on the previous slide. And that is to start at Pluto's radius that was measured by New Horizons, which was at 1,190 kilometers. And the surface temperature at 37 Kelvin, which is the frost temperature for nitrogen ice that you can hopefully ski on. And I put a curve or a little kink here. This is 20 kilometers altitude, or 20 kilometers above the surface, and that's at 110 Kelvin. And I had to do some mathematical tricks, not really tricks, but rather than have this being a sharp, like piecewise function where it's just a line and then another line like this, I made it pretty so that it would curve. But it's more than just about vanity. It's because when you start taking these derivatives, this is a derivative of the temperature, you need it to be smooth. And this is the second derivative, you need it to be smooth and not going off into infinity. You need those things in order to calculate the light curve. So, okay, let's try. First thing with that temperature profile was to least squares fit that power law model and see how that does. Well, the blue is what I started with. The green, the shading with the error bars, The shading includes the error bars that come from that least squares fit. These don't match at all. hopefully that was obvious, and that's not good for our method of using the power law to describe a planetary atmosphere, or at least on Pluto. Okay, so what happens when we try the inversion method? Oh, sorry. Oh, I knew I would do that. I did this when I was practicing. Sorry, back up. This is the light curve that came from. So remember when I was talking about calculating a light curve, the black dots are my calculated light curve, and I've added some artificial noise to it, so it kind of looks like a real observational data set, because they're always going to have some noise. This is a pretty good light curve in terms of its noise. It has a good signal-to-noise ratio. It's typical. It's based off of that occultation from 2006 that passed over Australia. And this blue line corresponds to, should have made, it was too hard to see green on top of that black, but the blue line corresponds to the fit, and you can see from your eyes, just following the blue line, that it does not match my artificial data set, and you can see the residuals down here. This is time, and this is flux. You can see the residuals down here. They're way, way off from zero. They're like 20% off. Okay, now let's look at the inversion temperature. Okay, it kind of works. The blue line is, of course, what I started with, and the black dots are the inversion, and these lines here indicate the error bars that come off of that inversion process. So we call this the inversion temperature. And it's doing okay. It does really well at getting the altitude of where this kink is, but it's kind of systematically offset to colder temperatures. And that's just from experience, and as you'll see as I'm going through the rest of this talk, that's just probably from this boundary condition just being wrong at the top. This is a total systematic offset of this inversion temperature compared with what I started with. Okay, my second case was I changed the surface temperature to be 45 Kelvin, and the reason I did this was because from the radio occultation that New Horizons performed, or the experiment that it performed, on one side of the planet it measured the surface temperature at 37 Kelvin, and on another part of the planet it was 45 Kelvin. So we had two data points, but let's try the other one. Okay, let's try fitting it to our power law model. No. And I promise this is not the same plot. I really did actually make plots for every single one of these. Let's look at our light curve. You can see by eye that's not working. Inversion temperature. Well, okay, I don't know why I'm not quite sure why it's doing this, but again, it's kind of got the right shape, but it's not. It's just not like there's something going on here. Probably again from experience, probably due to that boundary condition up there. Okay, my third case, we'll put the temperature back at 37 Kelvin. I promise these get more interesting as we go through. And I changed this height. I raised it up by 10 kilometers. Before it was at 1210 kilometers. Now it's at 1220 kilometers. Okay, what happens when we try to least squares fit it to the power law model? Doesn't work. Here's our light curve. You can see by eye. I promise this is not the same picture. I promise I did make pictures for every single one of these, and I checked. You can see by eye it's not working. It's about 20% off, 10% off down here. The inversion, no. Well, but it's neat that it gets it gets the altitude right, because we're at 1220 is where that kink is, and it gets the altitude right, but it's still systematically offset. And again, I'm thinking it's because of that boundary condition at the top, which is something I should test. Case 4. Okay, now I've put this kink down. Remember our default case was to have it at 1210. Last one was at 1220. Now we're down at 1200, so we've now lowered it by 10 kilometers. And the power law, any guesses? No. Light curve, no. This is I did make individual plots for all of these. And the inversion, nope. Nope. It gets the altitude right. It's the altitude of where it needs to turn over right, but it's systematically set colder. Okay, case 5. Okay, if the inversion temperature wants to be colder, let's try to make the temperature profile colder. Before this was at, so I reset the kink back to be its nominal value of 1210 kilometers. This was formerly at 110 kilometers. Now it's at 100 kilometers. Kelvin, K kilometers Kelvin. No. Okay, let's see what happens with our power law. No. Light curve, no. Inversion? No. It's again getting the altitude right. It's still just made it even more cold. It's just not working. Next case. Let's try to make it hotter. Not that I think that's going to help, because it's at 120 Kelvin versus before it was at 100 Kelvin, and the nominal case is 100 Kelvin or 110 Kelvin. No, the least squares fit to the power law doesn't work. There's our light curve. No. Nope. We didn't think that was going to work anyway. Okay, now we're going to get a little bit more exciting. Case 7. Whoa. So the bottom part is the same. It's starting at 37 Kelvin, the N2 frost temperature that was measured before New Horizons, but also by New Horizons. And then now at this king, instead of just having it going straight up, I have it going down. And what this represents is cooling by carbon monoxide in Pluto's atmosphere. And that was one of the things that the physical model predicted. That's out of order right now. So that's my inspiration behind this one. And then above, see up here at about, this is 600 kilometers altitude, so 500 or 1790 kilometers radius. And then I just have it be 70 Kelvin above that. It's just kind of basing it on that physical model. Okay, now, can the power law least squares fitting method work? No. Didn't think so. There's a light curve, still looks awful. And the inversion, trying to build suspense. No. Again, it's the right shape. It just needs to be moved down about 30 Kelvin. And I am my instinct says that it's probably that upper boundary condition. That's something that I will want to test in the future. Case 8, we'll do something a little bit more fancy. Put a little place here that's isothermal, and that is supposed to say, 100 Kelvin, 100 kilometers right there. We put a little isothermal spot before we make it go down. That's our power law, least squares fitting, nope. And this is our inversion temperature, not quite. Something you might want to notice that I didn't say earlier was that actually, see, this is where it actually starts to turn over to get it colder. The way that the inversion, well, I guess I did mention this earlier, the way that the inversion temperature, the inversion method works is it fits the top half of the light curve to that power law model, and then uses the rest of the light curve to get this inversion temperature. So actually with the inversion method, you're only getting information from the bottom half, because you can't reuse that information that you used for the boundary condition and then to use it for the rest of the temperature profile. So that's why these things tend to be lower in the atmosphere. And it's not, the boundary conditions aren't catching that decrease that doesn't even start till up here on this scale. Okay, and this is our final case. Hey, what happens when it goes up? That's kind of one of the things that we learned from New Horizons is, well, that CO cooling where I had it going the other way, going really cold. It's not that cold. But what happens if we make it be hotter in the relatively higher altitudes? Least squares fitting method to the power law model, no. light curve, no. And the inversion method, nope. Okay, well, let's do a sanity check to make sure that there wasn't like a bug in my code the whole time that I was doing all this fitting and inverting the light curves. So I call that case 0. So I started with the power law model. Okay, so now what if my inversion, if my least squares fitting method and my inversion method, they'd better work. That code better work if I'm starting with that code better be able to fit what it actually started with. And it does. That's good. The dotted line here is the original, what I started with, and the green is, or the solid line is the best fit curve, and the green shading is where the error bars are. So it's not exact, but it's within the error bars, so that's okay. And here's our light curve. And now this is what a nice light curve should look like. This black is my synthetic data. The blue is the best fit model. And you can see in the residual flux, it's just noise. We're at 0. This is what a nice model light curve should look like. So my method works. My code works. The underlying mathematics have some problems. So, and there's the inversion. Yeah. The inversion is kind of weird. It doesn't, it's, this kind of worked and it didn't, and at the same time it kind of didn't work. The blue is what I started with, and then of course this is the inversion temperature. And I'm almost certain that it's this boundary condition at the top that it wasn't working. So that's saying that using that power law method to fit the top half of the light curve and then doing the inversion, using that model to get the boundary condition at the top is probably not a good idea, but you probably could have figured out that from also when we try to fit the whole light curve with that power law model. So I've been talking about the inversion of the light curve that whole time that has a non-unique solution. Where we start with the observations, we have to make some assumptions about the shape or the boundary condition, and then we get a temperature profile out that's non-unique. This is an example of the work that I did in 2011 with the physical model, and this was so back when that power law model was developed. Remember, I said it was kind of for mathematical convenience. Well, also it was because in 1992 computers were much slower, and so least squares fitting is an attractive option where you want to have the least amount of computer steps in order to get your solution. So now that computers are faster, I can use a more brute force method and just calculate a whole bunch of these light curves, and then just compare it with the data, and find the minimum of the sum of the least squares difference just by brute force, by just saying where's the minimum, rather than the more elegant method of least squares fitting, which steps through the parameter space in as few steps as possible. So now that computers are faster, I can do this. I can do this almost instantaneously. If I use a more complicated model, like what I'm used to using is the models that have like winds and the whole circulation of the atmosphere. I can't quite do as many of those, but I can still do it with the brute force way. But the point is, I can do the forward problem. I can start with a temperature, and get a unique solution for the light curve, and find the one that best matches the data. So that's kind of that's what we need to be doing as a community is this forward problem. That's going to help. I mean, if you've got a junk model in the forward problem, the forward way of thinking is still not going to help, but that's part of solving the problem. This is the light curve that matches that study in 2011 with the 2006 data. See, this is a very beautiful light curve. I'm very proud of it. I didn't take the data, but one of my bridesmaids in my wedding did take the data. I made the blue curve. So The take-home message from this talk questions where your temperature profile came from. How was the data taken? What model was used to obtain the result? Was it a model that was least worst fit? Does that model at all describe planetary atmospheres? Was it an inverse or a forward problem? Just know when you're comparing temperature profiles from the New Horizons data to models or other sources of data, know the assumptions that went in behind it. And I'm going to stop there.
Thank you, Angela. Any questions from Angela? Yes, Cliff.
So now that we have the New Horizons data, can you get a better handle on the boundary conditions using the forward problem? The upper boundary?
So probably that data is actually not. New Horizons measured the temperature of Pluto's atmosphere in two ways, and one was using the radio occultation one. They did do two stellar occultation experiments. That data is, some of it's been downloaded off the spacecraft. Some of it's, or maybe some, I'm not exactly sure where they are in the procedure, but it's either still in the spacecraft or they're working on analyzing it. So yeah, in theory you could use that to measure that upper boundary condition, but really theoretically that boundary condition needs to go to like infinity. Of course, in practicality it's not going to go to infinity, so it's going to depend on how high New Horizons was able to measure. And I'm not sure offhand because they haven't released that data yet, so I don't know how high in the atmosphere it went. But yes, certainly that's an idea.
You didn't mention the central flash, which is seen sometimes when the observatory is right in the middle of the shadow. Would you explain that?
Okay, the central flash is, so I was talking about what happens when that drop in the light curve, that's due to the effects of refraction. The central flash is due to the effects of diffraction. So it's the planet is focusing the light. And if you remember from the video that I showed near the beginning of the two stars going around Titan, when that image went around the limb of Titan, that was due to the diffraction, and that would be observed as a central flash. So what that central flash is it focuses the light. If the occulting body goes right in front of the star, and if depending on the shape, this gets really complicated, but depending on the shape of the object, if it's a circle, it's going to be an infinite center flash, and you'll see a limb or an image on all sides. If it's an oval, you're going to see 2 or 4, depending on where you are. If it's other shapes, you can see 3, which is weird. So that the central flash doesn't give you as much information about. Okay, I didn't talk about that method, but the central flash gives you. It's most useful for knowing the shape of the atmosphere and just the size in general of the atmosphere. It can be useful if you have different wavelengths. I'm not going to go into that because it's a different talk. If you have different wavelengths that you've observed the light curve at, you can back out a temperature profile, but that's way beyond the scope of that talk. But for these purposes, the central flash is not relevant here.
My question is about the effect of the composition on the resulting calculated temperature profile. You didn't include that, did you? You just had kind of assuming a clear atmosphere with a certain density profile.
Yeah, it was there implicitly when I was moving that the top of the temperature profile to be warmer or colder. So if there's more methane in the atmosphere, it's going to be warmer. Methane both warms and cools at different wavelengths, but it tends to warm in the upper atmosphere. Also, if you have higher pressure, the way that we specify methane, because it's a concentration, if you have higher pressure, you'll have more methane molecules, and so it'll also be warmer. So it was taken into account implicitly. And then those temperature profiles where it was sharply going down, cooling at upper altitudes, that's the effect of a lot of carbon monoxide in the atmosphere. So I was taking into account implicitly. I could have used the actual physical model to do all these tests, but since they're still reworking it from what New Horizons learned. I didn't want to use a model that's kind of out of date, and I just went with the most basic idealized temperature profiles.
Okay, any more questions? All right, well, thank you very much, Angela. And with that conclusion, we do the presentation of the highly coveted SETI Speakers Talk mug.
Thank you. Thank you.
There you go.
I have one of these from the last time, but it's not this. It's a
See,
different.
it
So now I got
changes.
two.
Now you've got two.
Now I've got two. Great. Thank you.
Thanks very much, everybody. We'll see you next